Hello everyone, welcome back to the series of complete DSA using Python, specially designed for GATE, data science and artificial intelligence. In this session, we will discuss about the asymptotic notations. Asymptotic notations are nothing just the mathematical way to represent the complexity of an algorithm. The complexity can be space complexity or time complexity. So let's master this amazing concept of asymptotic notations. Starting with the definition of asymptotic notation. So here is the definition. Asymptotic notations are mathematical way of representing the algorithm's complexity. So we can represent either space complexity or time complexity of any algorithm by using the asymptotic notations. And another important point about asymptotic notation is that asymptotic notations always find out the complexity, always represent the complexity in term of large size input. How much large? N tends to infinity. Means for smaller inputs, we do not consider how much time the algorithm is taking. For larger input, how much time that is taking, that is considered as the time complexity or space complexity. Fine, okay. Let's see different type of asymptotic notations. There are actually 5 type of asymptotic notation. First one is the big O notation, represented with big O symbol. Second one is the big omega notation, represented with this octopus like symbol. Third one is the theta notation, represented with theta symbol. Next one is the little o. There is a small o over here. Okay. Next asymptotic notation is the little omega, represented with this W like symbol. Okay, fine. Okay, so these are the 5 different asymptotic notations. These symbols or these notations have some specific meaning. Okay, we need to know the meaning of these symbols. That's it. If we know the meaning of these symbols, then we can use it anywhere. We can use it to represent the complexity of an algorithm. Just we need to know the meaning. So let me tell you the meaning of these symbols. For example, I'm taking one example, okay, over here. For example, somebody is saying that, sir, I have written one algorithm 1. And that is taking big O of n square time. He is telling me this thing. He is saying that, sir, my algorithm is taking big O of n square time. Then see what I will understand from this statement. Because he is using big O notation, from big O notation what I will understand? What I will understand is that he is trying to say me, sir, give any input to my algorithm. Any input means, for example, this algorithm is for sorting. This algorithm is for sorting the numbers. He is saying me that, sir, give the number in increasing order. Give the number in increasing order as an input. Maybe in decreasing order, okay. Maybe in decreasing order. Or maybe shuffle it. Shuffle it whatever way you want. Shuffle the numbers whatever you want. Give any type of input to my algorithm. My algorithm will not take more than n square time. That will maximum will take n square time. Maximum. So big O notation is telling us about what is the maximum time taken by an algorithm. You give any type of input, the maximum time taken by this algorithm is n square. This is what big O notation is telling us. Or in simple language, we can say that big O notation is telling us about the worst case time complexity. Worst case time complexity of an algorithm. Please note down, this is not telling us about the how much minimum time the algorithm 1 will take. I don't know. From this statement, I cannot say anything about the minimum time. But I can say one thing due to this symbol that, okay, this symbol always tell me the worst case time complexity. So this statement means is that for any type of input, the algorithm maximum will take n square time. So this is the information what we are getting from this symbol. Now you can use it anywhere with this information. Fine, okay. So big O notation represents the worst case time complexity. Now let's check out the big omega. So let me write one example over here for big omega. What do you mean by big omega notation? So if somebody write the somebody write the, okay, let me bring back my screen. So okay, if somebody use the big omega notation, then what that means, let's try to see. For big O, the meaning is worst case, that is showing the worst case time complexity. Let me check out for the big omega. Somebody is saying that, sir, I have written one algorithm 2, okay, and that is taking this much time, big omega of n square time. Okay, what he want to say me from this statement? What should I understand? He is trying to say me, give any input, increasing, decreasing, shuffle the number, whatever way you want. You give the input in any way, the algorithm minimum time, this algorithm minimum will take n square time, minimum. This will not take less than this n square time, this will not take n time or log n time. This algorithm will minimum take n square time for any input, okay. So either you give the even element in increasing order to sort, still the algorithm will take n square time, like this. So I can say that, okay, big omega notation is telling us about the best case time complexity. What is the minimum time taken, best case time complexity of an algorithm? Okay, please note down in this also, this representation is not telling me anything about the worst case. I don't know what is the maximum time taken by algorithm 2 right now. I don't know. I just know one thing. This symbol is telling me that, okay, the minimum time taken by algorithm 2 is n square. This will not take less than n square time. This is the only information I am getting from this symbol. Okay, fine. Okay, so now let's move to the theta notation. So we use the theta notation whenever worst case is equal to best case. If the worst case time complexity of an algorithm is equal to best case time complexity of the algorithm, then we can use the theta notation. For example, I can say that, okay, the best case time complexity of algorithm 2 is n square, and for the same algorithm I'm writing algorithm 2. The worst case I'm using big O notation to represent the worst case time complexity. For example, that is also n square. Both are n square. Best case and worst case both are n square. If both are same, best case and worst case both are equal, then I can say that, okay, algorithm 2 is having how much time complexity? Theta of n square. So rather than writing these two statements, I can replace these two statements with single statement. So simple theta notation is saying that when best case is equal to worst case, then rather than using these two notations, use single notation, theta notation. Theta notation says that the best case and worst case of this algorithm is same, that is n square. That's it. Please note down, many students make this mistake, is that, okay, they says that theta notations take average time complexity. Theta notation represent the average case time complexity. No, big no. Theta notation do not represent the average case time complexity. I have seen on many popular platforms and many YouTube channels also, they are saying that, okay, theta notation is average case. No, big no. Okay, so theta notation is used when worst case is equal to best case. Only then. Might be, okay, I can show this thing with one example. We cannot use the theta notation for average case. Okay, for example, okay, let me show you with one example this thing. Let me take one example. So I can take the example of one popular sorting technique. Actually, if you don't know, you can note down that, okay, quick sort. Quick sort is the best sorting algorithm. Okay, quick sort. So if we talk about the best case, average case and worst case time complexity of quick sort, so best case is n log n. You can note down. If you don't know, you can note down. Average case is also n log n, and worst case is n square. See, what I can say about the quick sort, the time complexity of quick sort is big omega of n log n. This statement is right. Because the best case time complexity of quick sort is n log n. Yes, I can write this statement also. The time complexity of quick sort is big O of n square. This statement is also right. This statement is also right because the worst case time taken by quicksort is n square. But if I am writing this thing, the time complexity of quicksort is theta of n log n. This statement is wrong. This statement is wrong because best case and worst case are not equal. Okay, so I cannot represent the time complexity of quicksort as theta of n log n, although the average case is n log n. Okay, so this is wrong. We can represent the time complexity of an algorithm by theta only if worst case and best case is same. We can do that in case of merge sort. If you know the merge sort, in merge sort, best case, average case and worst case all are n log n. So in case of merge sort, I can say that okay, the time complexity of merge sort is theta of n log n. Not because of average case is n log n, because merge sort, best case complexity and average case complexity is same, merge sort, that is n log n. Okay, if you don't know the time complexity of this, you can note right now over here for the quicksort. We will cover the quicksort in very detail in future lectures, in very detail. Right now you can note just one thing, that okay, theta notation is used when worst case and best case complexity of an algorithm is same, then use the theta notation to represent its complexity, but that is not showing the average case complexity. Okay, fine. So I hope this is clear. Now I'm moving on with the next notation. Even before moving the next notation, let me represent some more information over here about big omega and theta notation. So let me add some more information. So big O notation also gives one more information. What is that? He says that right hand side, whatever function we are writing at the right hand side, will be greater than equal to left hand side. So this is one more information big O notation tell us. Okay, so we will see that with one example, but before let me write. Big omega notation says that left hand side is greater than equal to right hand side. Okay, so if we are representing two algorithm, if we are comparing two algorithm, then with the help of these statements you can identify which is performing better, which is performing less. In the case of little o notation, actually little o is similar to big O. Name itself is, this is also O, this is also O, but this is little o. Okay, so this also have something like this relation. So let me write, left hand side is strictly smaller than the right hand side. Okay, here equal to is here, equal to is not here. That's it. This is the only difference. In the case of small o, which is somehow related to big O, see this thing and this thing is same, just equal to is not here. So I can say that little o is showing that right hand side is strictly greater than the left hand side. Okay, little omega notation is somehow similar to big omega notation. Name itself omega. So here this is taking this relation, but equal to is not here. So what little omega says that left hand side is strictly greater than the right hand side. Okay, so this is the relation given by the little omega notation. Everything will be very clear. I have lots of examples with me. We will cover lots of example, and after this session one thing is sure, you will be very well knowing all these notation. That is confirmed. Okay, fine. Okay, let me take the example and go through all of these information. So if I am writing that, okay, algorithm, let me write over here. Algorithm 1 is taking n time, fine, and algorithm 2 is taking n square time. Okay, fine. So I can represent the relationship between algorithm 1 and algorithm 2 by big O notation. Yes, I can represent that. Okay, I can represent that because this big O notation can be replaced by this relation, actually this relation. So if I replace this with this, so you are finding that okay, algorithm 2 is either taking greater or equal time to algorithm 1. Yes, algorithm 2 is taking n square time, which is bigger than n, actually, which is bigger than n. Functionally that should be greater. Functionally means not by any constant, but functionally here this is Actually n square is n into n and n is n only. So this is n times greater than this. So yes, this is functionally greater than this. So simply replace this symbol with this and check out, is this relation working? Yes, that is working. Even though I write n square here, still this relation is very fine, because we can replace big O with either with this or this. Any one relation satisfied, then I can use this big O notation. So yes, both are taking m square time equal to. Equal is there. So I can represent the relationship between algorithm 1 and algorithm 2 with big O notation, because this is allowing us that okay, right hand side can be greater also, or that might be equal also. In both the cases we can use the big O notation. Okay, that's it, what this is saying. Okay, big O notation. So this way we can relate two algorithm with the help of big O notation. So by using this statement actually. So this statement is coming all by mathematical. I am just providing you directly this statement to you. You can take it and you can use it to solve any type of problem. In the next session, we will solve all the previous year questions from I think 1994 till today. We will solve all the previous year question with this information only. We will not be requiring any other detail to solve any of the gate question. Okay, I'm providing you sufficient information. Fine, okay. So we can compare two algorithm by big O notation if this condition satisfy. Yes, this condition satisfying over here. So algorithm 2 either will be greater than algorithm 1 or might be equal also. So in both the cases we can use the big O notation. This is the only thing I tell you. Now I'm moving with the second relation, that is big omega notation. So let's suppose here we have n only. Let me write n only. Here we have n. Algorithm 1 is taking n time. Algorithm 2 is taking n square time. So can I represent the time complexity like this? Let me erase this one and write another relation in context of this. Can I say that okay, algorithm 2 is equal to big omega of algorithm 1. Algorithm 1. Yes, this statement is right, because I can replace this big omega by this relation. So I can write greater and equal. So left hand side will be either greater or equal to right hand side in the case of big omega notation. So if this type of relation is there between the two algorithms, we can represent the relation by using the omega notation, big omega notation. So let's check out if this relation is satisfying. Yes, algorithm 2 is n square and algorithm 1 is n. So n square is greater. Yes, that is greater than n. So we can represent the relation between algorithm 2 and algorithm 1 by using big omega notation. We can represent. Why? Because yes, left hand side is greater than the right hand side, that is greater. So we can use the big omega notation. Even both are n square. Still we can use the big omega notation to show the relationship between these two, because they are equal to is also available with us. So either both algorithms are equal or left hand side is greater. We can show the relationship between them by using the big omega notation. That's it. This is all about this condition. So this condition is just telling us, can you show the relation between two algorithms by using big omega notation? Only when left hand side algorithm is taking either more time or equal time to the right hand side algorithm. That's it. This is the only thing you need to know. Let's move on to the theta notation. So what about theta notation? See, this relation right now I can represent with theta notation also, because both are equal, exactly same, n square. So I can write algorithm 1 is equal to theta of algorithm 2. So either way, algorithm 2 is equal to theta of algorithm 1. Both are same thing. When both are equal, functionally, again I am saying functionally, constant factor we can remove. In asymptotic notations, we throw away the constant factors and lower order terms, because we always find the time complexity for large input. Constant factor will not make the impact for large input. Okay, or lower order terms will also not grow with that much speed. How much higher order terms is growing for large input. So because of this large input, we are throwing both of these terms, lower order terms and constant factors, only considering the factor which is consuming most of the time, maximum time. Okay, whenever we find out the time complexity, we consider the factor which is impacting more. Even that is satisfying our definition of time complexity which I give you. What is the definition? Finding the time complexity means finding that part which is taking maximum time. So we are only bother about the bigger term, not smaller one, due to this thing, because we always consider large size input, and for large size input, constant do not make impact, lower factor do not make impact. Fine, okay. So theta notation we can use when both algorithm taking exactly same amount of time. Exactly same amount means asymptotically they are same, means both are taking functionally same amount of time. Constant factor is coming, we can remove. Still this is same. If I am writing plus 10, still there can be represented with the help of theta notation, because constant can be removed. Even if I am writing plus n, lower order term, we can remove this also. So lower order term and constant we can remove. After that, yes, these are matching, so we can represent with theta notation. We have lots of example with us. I will go through them also. That will bring us crystal clear clarity in our mind about the asymptotic notations. Keep taking it, what I am telling you right now. So I've just tell you, till now I just tell you that, okay, big O notation shows the worst case time complexity. Theta, big omega notation shows the best case time complexity. Big O notation shows this relation, saying that right hand side will always be greater than left hand side. Okay. So even though you are saying that big O notation, you are saying that, okay, some algorithm is taking big O of n square time. So this is matching with the definition also. This thing intuitively you can take, directly take the intuitively will work in the gate exam. Okay. So this relation is saying that, okay, n square is either, I am replacing this symbol by this. N square will be either is greater than this or equal to this. And our definition, what we discussed earlier about big O notation, is that this algorithm will maximum take n square time. Yes, algorithm is either smaller or equal. Maximum that can go up to equal to n square, but not more than that. So intuitively also, this statement, this condition is matching with the definition. Definition is also saying the same thing. Big O notations simply provide us the information that this person is either greater or equal to this person, means this algorithm will take maximum n square time. So that will be either less than this time or either equal to, maximum up to that will go up to n square. So this is intuitively you can take. You can take this also same way intuitively. So let me write it over here. Take it intuitively, that thing will work only. Just going through cramming the stuff and going through complete proof is not required. What is required? If you are understanding that intuitively or not, this thing understanding intuitively or not. So let me go through intuitively again. This is also saying the same thing. See, if I am writing algorithm, let's suppose algorithm 1 is big omega of n square. So the definition of big omega says that the algorithm will take minimum n square time. And if I am replacing this with this is also saying the same thing, that, okay, my algorithm will either take more time than this or maximum equal to this, but not less than this. So this statement is matching with the definition. Definition says that algorithm 1 will take minimum this much time. This will not take less than n square time. And this, if I am replacing this with this is also showing the same thing. See, think intuitively. Algorithm will take either more time than this or maximum equal to this, but not less than this, not less than this. Same, what is the definition of big omega notation? So yes, this is right, this is right. These two things will work. And this is the only information required to solve every question in the GATE exam. Okay, fine, I'm moving on. Theta notation we use when left hand side is equal to, when, let me write over here, here we have space, left hand side is equal to right hand side. Means left hand side algorithm is taking exactly same time what right hand side is taking. So if both are taking n square, we can represent the relationship between algorithm and algorithm 2 by using the theta notation. Yes. What about little o and little omega? they are not also, I can say that, okay. So for example, if I write n over here, so let me erase it all to make the space for explanation. Let me erase this part up to here. Fine. Let me go through this little o notation. Little o is if these two algorithms are given to us, I can represent the relationship between algorithm 1 and algorithm 2 by little o notation, okay, like this. Algorithm 1 is equal to little o, little o, little o, little o of okay, algorithm 1 is equal to little o of algorithm 2. Yes, this way we can represent, because we know that left hand side should be less than right hand side. Right hand side, or you can vice versa also, you can say right hand side is strictly greater than left hand side. Yes, n square is greater than n functionally. Functionally means this is actually n into n and this is n only. So this is n times greater than this n. So yeah, this algorithm 2 is functionally greater than algorithm 1. Okay, so we can show the relationship now with little o also, although the same relationship can be represented with the help of big O notation. So this is also fine. This is also fine because big O notation says that that can be greater or equal, both are there. Here only greater is there. But if you see carefully, okay, if you will see carefully over here, this is the important point over here, and difference also when to use little o, when to use big O notation. So see over here, I can represent the relation between algorithm 1 and algorithm 2 by both little o and big O. Yes, that is right. But it's better to represent this relationship right now, the between n and n square with little o, because n square is strictly greater than n. N square is strictly greater than n. If I am representing the relation with big O na, then there will be one dilemma in my mind. Okay, if I do not tell someone that okay, how much time this is taking, how much time this one is taking, I just tell them this relation, big O relation between them. I can tell because big O notation also have equal to, but he might think this thing that okay, algorithm 2 can take more time than algorithm 1. Yes, but that can be equal also. Maybe both are performing equal. Okay, both are performing equal. But in this case, both are not performing equal. If we are sure that algorithm 2 is taking more time than algorithm 1, then why to use this notation? It's better to use little o notation, because this is giving us more better information that yes, we are sure algorithm 2 will take more time than algorithm 1. Okay, fine. When equal is not there, then it's better to use the little o notation. When we are sure that this is taking more time than this, then it's better to use the little o notation. Fine, okay. So this is about the little o notation, more than enough. We will practice more question on this, but let me go through the last notation first, that is the little omega. That is same as the this big omega notation. So if I want to show the relationship between algorithm 1 and algorithm 2, I can write like this. Here left hand side should be greater than right hand side. So let me put the bigger one to the left hand side. Algorithm 2 is equal to small omega of algorithm 1. Algorithm 2 is equal to small omega of algorithm 1. This statement is right. Yes, n square is greater than, strictly greater than n. Yes, this statement is right. I can represent the relationship between algorithm 1 and algorithm 2 by using big omega also. So let me write over here, algorithm 2 is equal to big omega of algorithm 1. Why I can write this? Because I know that this big omega shows this relation, that greater than equal to. Yes, this statement is right. N square is greater than n. They are not equal, but they are greater. Anyone is satisfying. Anyone is satisfying, either greater or equal. Either greater or equal. So yes, the relationship between algorithm 2 and algorithm 1 can also be represented with small omega and with big omega. Then which one to use? So in this case, it's better to use the small omega. Why? Because this is strictly greater than this. If I am using big omega, there will be a question in my mind that might be they are equal, but they are not equal. N square is, yes, definitely greater than n. They are not equal at all. Why use the big omega? Why create this dilemma in mind that okay, they might be equal? Okay, so now you must be understanding that okay, when to use the little omega? Whenever left hand side function is strictly greater than the right hand side. Okay, so whenever you want to represent the complexity and you are sure that your algorithm, let's suppose algorithm 1 is taking okay, maximum n square time, then you can say that okay, you can say that algorithm 1 is equal to maximum. If this is taking this much time, then you can say that that is small o of n square, maximum if we are talking about. And if we are talking about minimum, if you say that your algorithm minimum, okay, let me make the space over here and wind up this. So this is, I talked about the little o now. So if maximum time taken by your algorithm is n square, so you can write like this way. Okay, you say that okay, your algorithm, if you are sure that the algorithm 1 will not reach to here, that will not equal to this. If we are sure that that will not take n square time, but that will take less than n square time, that is confirmed. Okay, that will take less than n square time. That will not equal to algorithm 1 complexity will not equal to n square. Okay, that will be less than n square. That might be n, that might be log n. So in that case, we can use the little o notation. Okay, and if we are sure that okay, the minimum time, let me write algorithm 2, the minimum time is, your algorithm will not take even n time, I can speak like this way, even n time. So I can say that okay, algorithm 2 is equal to small omega of n. Okay, we are sure that even algorithm 2 will not reach to the n, that will not reach to the n itself. So that will take more than n time, more than n. So maybe n log n and all that, but that will not reach to this lower limit also. Definitely that will not reach to n. So then we can use the little omega notation. Fine, okay. This is all about the different asymptotic notation. Don't need to worry. We have lots of example. I will take 20 examples right now, and after that everything will be better crystal clear. With the example, this goes very smooth even. So this is the all definitions I give you, and the maximum you need to know from the asymptotic notation. Now you can use it your whole life. Don't need to study anything else. Fine, okay, let me erase it and let's go through the different examples, practice questions. So it's practice time now. My advice to you people that okay, for better learning, please pause the video and try it yourself first. Okay, I'm trying it these question at my end. Before that, so these are the some 5 practice question. You need to reply true and false. Which statement is true, which statement is false, you need to tell. Okay, so some notations I'm using, we will be able to understand when to use which notation. Okay, what is the use of that notation, this notation, what is the difference between them, everything will be clear. Try it yourself, pause the screen, try it yourself. Meanwhile, I'm also writing, okay, what we learned in big O notation. We discussed that big O notation represent the worst case time complexity. One is this thing we discuss. Second thing is that okay, left hand side is less than equal to right hand side. Big omega notation, what that information is providing us, that is representing the best case time complexity of an algorithm, and left hand side will be either greater or equal to right hand side. These two information we get. About theta notation, in theta notation we understand that okay, we will use the theta notation when worst case time complexity of an algorithm is same as best case. And second information what we get from theta is left hand side is strictly equal to right hand side, is equal to right hand side. When they are equal, then we can use the theta notation to represent the relationship between those two people. Next one is okay, so I think I need to rewrite it again. This get erased. So let me rewrite. My pen is gone. Let me take the pen back. So just I write that, okay, big O notation shows the worst case, left hand side is less than equal to right hand side, and big omega shows the best case, means left hand side is greater than or equal to right hand side. And if we talk about the theta notation, in theta notation, worst case is equal to best case, okay, then we use the theta notation, or left hand side is exactly equal to the right hand side. Another notation is the small o notation. In small o notation, we know that, okay, we use that when left hand side is strictly less than right hand side. And last one is the small omega, in which left hand side is strictly greater than the right hand side. So this is the only information needed to solve all this problem, and we will be able to understand all the asymptotic notations. So let me try it at my end, you people please try at your end. So is this relationship right or wrong? So big O notation, we know that, okay, that shows that, okay, right hand side will be either greater or equal to left hand side. Yes, right hand side is greater. Any one can be true, either greater or equal to. So yes, n square is greater than n. This statement is true. Both are equal. So big O notation can also be used when both are equal. Equal is also allowed. So this one is also true. Here left hand side is greater than right hand side. This is not possible in big O. In big O, left hand side either will be less or equal to right hand side. So right hand side will always be greater or equal to left hand side. So this statement is false. Left hand side cannot be greater than the right hand side in big O notation. This one, okay, remove the constant, don't need to worry about the constant. So here n square is greater than n, yes, right hand side is greater, this is true. Big omega, so left hand side is greater than right hand side, yes, this is allowed, left hand side is greater than right hand side, so this is also true. Fine, okay, these are the next 5 examples. I'm trying it at my end, you people try at your end, pause the video and try it, then check out the solution. That will work much better. Here both are equal, left and right, yes, equal is also allowed, anything, either left hand side is greater or equal to right hand side, so this is also true. This relation is false because right hand side cannot be greater than the left hand side in big omega. Right hand side cannot be greater than the left hand side, so this is false. Remove the constant and check. Both are equal, n square, true. Equal is allowed. Equal is allowed in big O and big omega, okay. Theta notation, both are equal, yes, they are exactly equal. Equal is allowed. Only if exactly equal, it's better to use the theta notation, okay. If exactly equal, if we know that they are same, exactly same, then it's not a good idea to go with the big O and big omega. Big O and big omega, it's better to go with the theta notation. So this is true. This is false because they must be equal. They are not functionally equal. N square is not equal to n. Next one is they are equal, yes, this must be true. Remove the constant, check out. They are not equal, so this is false. Little o says that right hand side should be strictly greater than left hand side, yes. N square is greater than n, yes, so this is true. Both cannot be equal. Equal is not there in small o notation, this is false. Right hand side is greater than left hand side, yes, n cube is greater than n square, this is true. Let me take more example and try it. Remove the constant and check out. They are equal. No, equal is not allowed in small o notation, this is false. Here small omega, left hand side is greater than right hand side, yes, n square is greater than n, this is true. Both are equal. Equal is not allowed in small omega and small omega and small o, so this is false. Left hand side is greater than right hand side, true. Remove the constant. Both are equal. Equal is not allowed in small omega, this is false. So that's it. So we gone through all the 20 examples also. You can try it yourself, and if what you people can do one more thing, you can go through this video one more time if you want. If you finding little anywhere, anything if you are finding missing, if you will go through once again, you will get it again back. And one thing I can assure you that, okay, this video is more than sufficient for asymptotic notations. In the next video, with this information only, which is written downside, with this information only, we will solve all previous 30 years PYQs we will solve all the asymptotic notation problems. This information is more than enough to solve all the PYQs. Okay, fine. Okay, let me erase the board and move on. Yes, that's it for this session. Stay tuned. We will meet back in next class.